it more or less than the equivalent prototype? It's more. Okay, and that's because you're applying the same pressure head on a much shorter seepage distance. So it makes sense. Good. What was that third one? I forgot.
Impulse.
Ah, what did you think of that?
Square.
N
Square.
and square. Okay. So we got that. Excellent. So those are all more straightforward things to do. Today we'll start by looking at the earthquake business in centrifuges, and then we shall launch ourselves into file design. Okay. Although we are going to focus on earthquakes, the same scaling laws and technology, if you like, can be applied to other types of dynamic loads, for example, blast or wind, any dynamic load which varies with time. You should be able to model this entity quite nicely, especially for blast loading. Because the way energy scales, that's something you can derive again as part of your newfound scale. That if you find the scaling law for energy, you will see that it scales as n cube, which means in a centrifuge we can have really small amounts of explosives, and you can model something that is much bigger, n cube times bigger. So at 100 G, say if you're doing these tests, it's 100 cube will be how energy scales. So it's a big advantage to model explosions in a centrifuge. In fact, the whole business of centrifuge testing in Soviet Russia started that way. They wanted to model big explosions in the centrifuge so that they understand how, if the Americans ever bombed them, what damage they would do. And so it's a very useful application there. Finite element analysis in comparison is complex and often requires specialist codes. You will get a chance to play with the flaxes. There's also flags, and there are other codes. But again, as I said yesterday, you need to know the constitutive model you're using and how it is going to behave under the particular type of loading. We saw these sand balls yesterday, but what I like to focus on is we're trying to model an event that is fairly violent. It's turning ground effectively into liquid for a short period of time. On the computer or? Yeah. Yeah. That's better. Okay. These samples, by the way, were what we recorded in Bhuj. It's the only earthquake I know where after the liquefaction, you could spot them even many months afterwards because of the salt water. All the salt water came up, and all this, the white stuff you are seeing is salt. And that's stayed because it doesn't rain much in Kutch. There's a lot of these sand balls stayed for a very, very long time. Normally, you get a rain after the earthquake and all the evidence of liquefaction is lost, but not in Kutch. And you may have seen this is another interesting problem actually, where these images are from Taichung. harbor, but these seem to happen in almost every harbor after liquefaction, including our Kandla port, where the ground liquefies and the tanks which are holding either petroleum or any liquids tend to lose their tops, and that's because the way in which the liquid is sloshing inside a cylinder means it tries to oval and buckles the roofs. So if you look at the roofs of those uh, con- tanks, you can see those are completely destroyed because of the liquefaction. There you go. You see those. So more images of this. So our main idea of trying to do dynamic centrifuge tests is we want to create those kind of realistic failures in the centrifuge. So we want to do this at small scale and have earthquakes whenever you want, not whenever they happen. And try the main idea is that we can put instrumentation into our models and observe the mode of failure. The best thing you can get out of a well-conceived centrifuge test is the failure mechanism. And I'll give you examples with files later on. But for any problem, when you start new, that's what you're aiming to do. You're aiming to capture the failure mechanism. Once you know the failure mechanism, then you can run the numerical analysis or any other limit equilibrium analysis even, because you know you're uh, capturing the right failure mechanism. Also, we tend to use the results from the centrifuge test to validate numerical models. And again, there are many papers in literature which do exactly that. At the moment, there's a big project going on called LEAP project, Liquefaction uh, Experiment and Analysis project, between about on last count, 15 universities. Ourselves in Cambridge, Davis, RPI in the States, uh, three Japanese universities, 4 or 5 Chinese universities, a huge bunch of us, and the Koreans as well. We're all trying to do the same experiment in different centrifuge centers and compare the results. If I have time, one of these days, I'll explain a little bit more about that project. Right. Coming back to the basics, what do we understand by earthquake load? What is it that we are trying to model? You all know that earthquakes happen because of a fault rupture. So you have a fault in the foundation rock somewhere, and that slips. And as it slips, it creates lots of body waves which propagate in all directions. Our problem will limit ourselves to the arrival of these waves at the bedrock. Okay, and from the bedrock here, so these waves arrive, and every point here is shaking in the horizontal direction. The biggest damage we worry about is the propagation of what we call the SH waves, the horizontally polarized shear waves, which propagate upwards. And as these do, every particle here is shaking horizontally, and that's what gives us our earthquake motion to the structure. At the end of the day, we are worried about what these things do to the structure. And our 1G is in this direction, of course. So we are trying to model this. So let's do some basic equilibrium equations. Uh, if you take an element of soil, if I go back, suppose I consider a little block of element there, and I draw the stresses on it. I'm going to have the vertical stress, the horizontal stress, and the shear stress. So if I can write the equilibrium equation simply as the spatial variation of horizontal stress and shear stress plus x in the x direction, and similarly y in the y direction. So these x and y are the body forces. Now let's assume that I can represent somehow the displacement that is seen in this element as a sine omega t. The minus is just to give it positive accelerations. It doesn't really matter. So if I differentiate that twice, if I differentiate it once, I get velocity. Differentiate it again, I'll get acceleration. Okay. What about body forces? The body forces in the y direction we already know. Thus, simply the density times gravity. And in the x direction, it should be mass times acceleration. So the mass is given by the mass density rho, and the acceleration is a omega squared sine omega t. So if I plug these back, so this is all good for prototype, right? For the model in a centrifuge, what should happen? Now the accelerations are something we already know. Why? Because we in the yesterday's class we said of course the gravity must be increased by a factor of n in the centrifuge test, but gravity is acceleration, right? That's why it's called acceleration due to gravity. So we should be consistent. So immediately our acceleration should be not a omega squared sine omega t, but it should be n a omega squared. Also notice I had to add this n to the frequency. Now, if you run with that for a second, I can now integrate that to get velocity and integrate again to get displacement. And velocity turns out to be a omega cos n omega t, cos n omega t, and displacement is x is a over n sine n omega t. So basically, by making the frequency n, we got rid of the extra n I was getting there. Now we also notice that the displacement amplitude A is now being divided by n, which is right, because yesterday also all length parameters must be scaled down by a factor of n. So by increasing the acceleration by a factor of n, we got the right displacement as well. The only problem is that this frequency has to go up by factor of n. Now this has some unfortunate consequences for us. As I said yesterday, the earthquake shaking is fairly gentle affair, 1 to 5 hertz, 1 cycle or even 5 cycles. Not very quick. This multiplying by n means if I want to model an earthquake which is 1 hertz in a 50G test, I must shake at 50 hertz. And this is quite difficult. And this is why these earthquake actuators are such complex machines compared to a normal shaking table, which the structures guys use all the time. And they're very easy to build in them. Now, let me tabulate all the scaling laws. So you have the ones we got yesterday, and the ones in the board are the ones we added today. The velocity, acceleration, now the frequency, and once the frequency goes up by a factor of n, the time period comes by a factor of n. This is also unfortunate for us. Why? Because a real earthquake, let's say, lasts about 30 seconds or 40 seconds. In the centrifuge, you need to deliver the same force in 1 over n times of the real earthquake. So the earthquake in the centrifuge should only last about, say, half a second. So you're asking to shake at higher frequency and deliver the same energy in a much shorter time. And energy over time is power. So the power of the shaker needs to be quite big. So you need The other thing is from data acquisition point of view. From a data acquisition point of view, you have to log, suppose a typical centrifuge test has maybe 50 or 60 instruments in it. You have to log all the 60 instruments at a high enough sampling rate to capture what's going on, right? So if my entire earthquake lasts only half a second, I need to be logging each channel or each instrument at maybe 5 or 6 kilohertz. And if there are 60 of them, I need a throughput of 360 kilohertz. All this stuff I learned on my own, because when you train as a geotechnical engineer, you have no idea what the heck all the signal processing guys are doing. And you learn very quickly. There are some very nice books you can read. But that is the extra complication of trying to do these things in the centrifuge. So it's not all bed of roses, centrifuge testing. There are things which actually you need to think about carefully. So this is the same thing in words, if you like. We need, usually we're aiming to model earthquakes 1 to 5 hertz, maybe 20 to 90 seconds would be a typical earthquake. But I showed you some yesterday. And we need to shake this while the thing is spinning around at about 200 miles an hour. We need the rotation to get the radial gravity field. And while the model is running around, you need to shake it. So the shaking table has to be on the centrifuge. Now, again, these are just in words. We can give you these slides later on, so you can go through that. Actually. Now, there's always this question about what type of earthquakes should we be modeling. Now, we could do sinusoidal motion, and what people generally consider is having something like 10 cycles of strong shaking is too much. Okay, which is typically what we were doing in Cambridge for 10, 15 years during my PhD time and later on as well. And the reason is we want to fail the model, and by failing the model, you get to see the failure mode. And that, as I said, that is getting the failure mechanism is the ultimate aim in all this. And as a result, doing sinusoidal motion is obviously quite strong and it's quite good at doing inducing a failure. Real earthquakes, on the other hand, typically have maybe 2 cycles or 3 cycles of strong shaking and a lot of rumbles afterwards or before. The other advantage, the bigger advantage of doing pure sine waves or tone bursts is you know the frequency at which you are putting the energy into the system. So if the system then responds with whatever it wants to do, you can easily detect the changes. For example, say you have a structure and the structure has some eigenfrequencies. You're aware of that, I hope, eigenmodes and eigenfrequencies. And you deliver the energy at half the eigenfrequency. It does one thing. You deliver the energy, the same energy at exactly its, say, first mode eigenfrequency, it will respond wildly, right? Because it's resonating. So you can track the response of the structure by applying series of sinusoidal waves at different frequencies. Another way you can do that is to roll down what you call Sine Sweep. Again, that with some signal processing, you can pick up the resonant frequencies quite well. And all our work on solid structure interaction relies on doing something like that. However, if you talk to our structural colleagues, they're completely wedded to the idea of designing structures based on response spectrum. So all they talk about is, can you guys deliver an earthquake which has a particular response vector. Even codes of practice. If you go to Eurocode 8, you can see that there are specified response spectra for, I think, the entire soil mechanics. They simplified into 3 or 4 forms: rock, dense sand, loose sand, and clay. And that's it. Like any subtleties in between, silts and all are thrown out of the window. But then most of these codes are being written by structural engineers. What do you expect? So, if you want to see what your structure is going to do for a particular earthquake, let's say, mostly we have motions which are recorded in past earthquakes, Kobe motion or El Centro, Imperial Valley. There are some standard earthquakes. And each of those earthquakes have some special characteristics. For example, Kobe has delivered almost all its energy in only 2 peaks, one very large peak and one relatively modest peak. The rest of the motion doesn't exist, really. Imperial Valley, on the other hand, is a very long earthquake and has quite a lot of high frequency content. So, if you want to study the response of a particular structure to these various types of earthquakes, you obviously can't rely on simply putting sinusoidal motions into that. So, we need to have both these capabilities, and that's where really our evolution in modeling has taken us. One thing I'd like to point out is, although it's nice to put these realistic motions, I'd like you to think about the soil as a material. Soil as a material is quite complex. It has this, it's highly nonlinear. It goes plastic, or you mobilize plastic strains at really small levels of shaking, which means that the material is changing its characteristic as the earthquake waves are going through it. Therefore, and this is again reflected in the amount of excess pore pressure that is generated as well. So the more shaking there is, obviously more cyclic strain amplitudes, therefore more pore pressure. Now, into this mix, if we throw the additional complexity of having a real earthquake, sometimes it gets really complicated. So having a clean, simple sine wave is preferable if you are trying to do really fundamental research. Then you can understand what the system is doing in response to your simple motion, because the system is a complex one. Now, one thing we have to address here, and then I can move on, is this question of time. Yesterday, quite nicely, I told you we invented a time machine, right? So when you did the consolidation scaling law, it came out in our favor of 1 over n squared. Today, I'm saying to you, having slept over it yesterday night, we are scaling frequency by a factor of n. As a consequence, the time period therefore scales as 1 over n, right? Frequency and time period are just 1 over the reciprocal of each other. Now, these two sit together. You got the scaling law for consolidation time or slow time as n squared for any diffusion process that is true, and you've got all these dynamic times which are scaling as a factor of 1 over n. So we have a factor of n missing between the two. Now, this is a real problem. You cannot have the same parameter, in this case time, scaling differently for one part and for the static part and differently for the dynamic part. That is going to make the centrifugal modeling impossible. And particularly for what we are interested in, which is the liquefaction issue, this is even more complicated or even more showstopping. Why? Because the excess pore pressures will be generated following the scaling law of 1 over n, and the dissipation then has to will happen n times quicker because there is that n factor again. So what do we do? So there are two things you can do. One was the question somebody asked yesterday that you can change the particle size or you can change the pore fluid. Let's do the later first. Let's look at the pore fluid. If I change the pore fluid and use a fluid that is n times more viscous, then my generation of the pore pressure will happen according to the 1 over n. But the dissipation will also be slowed down because the fluid is more viscous. So I can match the two scalings, generation and dissipation, by switching the fluid on the soil. Of course, you can't simply change the fluid and hope the soil mechanics does not change. You need to spend some time, which is what these guys, Eaton, who gets mentioned everywhere, John Eaton, I believe, he did his undergrad in Cambridge in 1975 or something. He's unaware that his name is so popular amongst researchers. He just finished his degree. I guess he's working for a bank or something. But the bit of fourth year project work he did, we still use. And that is what he's basically done is he's done some cyclic triaxial tests with water and with viscous fluid, in those days silicon oil, and showed that the constitutive behavior is exactly the same. In other words, the stress strain behavior looks exactly the same. This work was followed by Zhang more recently, my former colleague. And basically, we got enough data out there to show that the fundamental soil behavior does not change by changing the viscosity of the pore fluid. So we got some legs to stand on. This one, the bit that I have got in the slide here is I did mention you can change the hydraulic conductivity of a soil. One way is to change the pore fluid, and the other way is to reduce the particle size. If you remember Hazen's equation, it basically says it's about permeability is 100 times d10 squared or something. Now, if I reduce my d10, then I can change the permeability. So instead of using sand in the model, I can reduce the d10 size and maybe make it silt. The problem is that if you did that and did your, like Eaton has done, the triaxial test, you will very soon find by changing the particle size, the constitutive behavior changes. So you will basically shoot yourself in the foot. Although you can substitute the material and use something which is finer and has the right permeability, it won't have the right constitutive behavior. So that scaling of particles is not a good idea, which is what I was alluding to yesterday as well when somebody has asked. Who was it, by the way? Forgot? Yeah. Good. Now you have a bit more information why we don't do that. Very good question, by the way. My cough has returned, it seems. Earlier, to switch the viscosity, we used to use silicon oil. Silicon oil is quite non-toxic, and any material we use has to health and safety is a big thing, and silicon oil passes all those things. Later on, the only problem is it costs about 10 pounds a liter. 1 kilogram of silicon oil costs about 10 pounds. And typically each model we need maybe 30, 40 liters. So that was about 300 or 400 pounds worth of silicon oil we're using, and dig it all out and throw it away after the test. So in order to just keep the cost down, we discovered you can increase the viscosity using methyl cellulose. Methyl cellulose is basically food additive, and therefore it's quite safe. If you can eat it, it's quite safe because the food industry has quite strict limits on things, and it's a little bit of a pain to make it into a liquid, but we got kicked to do that. It's become quite cheap to use methyl cellulose compared to silicon. Okay. The other point is shakers. I talked yesterday, so I'm not going to focus on that. I didn't mention too much about the model containers yesterday, which we will talk about. So all the shakers, just wanted to say, I showed you a mechanical actuator, the SAM actuator, and the servohydraulic shaker, but there are other options as well. This is the SAM, which we have seen yesterday. I'm going to go through all that. But it is possible to have an electromagnetic shaker as well, which initially I was quite tempted to. And then I visited this company in Japan, who are the only ones in the world who have a working electromagnetic shaker. They're called Shimizu. And then I looked at their shaker and quite soon discovered this is not going to work in Cambridge. What the problem is that because of the power requirements, you need to put in close to 800 amps onto your electromagnet to get enough power to shake the model. The models weigh, say, have a mass of say 300, 400 kilograms. At 50G, they're going to weigh 50 times 300, which is close to 15 tons, right? So to shake something that is 15 tons at these frequencies, you need a lot of power. And the only way an electromagnet can produce that much power is if you increase the current. And if you need that much current on the arm of the centrifuge, all that has to go through a slipring stack, and that's a nightmare. So I've given up on that. But these guys have, Shimizu have one, and this is their picture, which it does work. The next point I wanted to focus on is the the issue of modeling something that is very big in a small scale. The biggest issue we should consider, especially in earthquake engineering, is the lateral extent of soil. We all call it semi-infinite half space, right? So horizontally, we expect the soil strata to run to plus infinity and minus infinity. Of course, this is just in relation to the structure you are studying. Nothing goes to plus infinity or minus infinity. We know that. It's just the size of our construction is relatively small compared to the dimensions, lateral dimensions of the strata. Now, what we're saying is, we're going to try and model that, let's say, in a box like that. Obviously, I can't make a box that runs to plus infinity, minus infinity, right? So we have to somehow make the soil think that it is going all the way on either side. By the way, it's the same problem in numerical analysis also. You need some form of absorbing boundary or non-reflecting boundary in the numerical analysis as well. So one way of doing this is this concept of equivalent shear beam box. So you make a box which has rubber, alternate layers of rubber and aluminum. Okay, and this way the box, you can match the dynamic stiffness of the box to the dynamic stiffness of the soil. So if the black, we can work out how the soil is going to oscillate in its first mode and draw the shape. So the black line is what we expect the soil to do for a given earthquake. And the rubber deforms, but the aluminum doesn't. So you can match in a stepwise fashion the black line. If you do that, the amount of reflections you get from the sides will be minimized. They won't be zero, but they'll be significantly minimized. Once we have done this little box, this box at say 50G can simulate something like 15 meters or 18 meters of soil. So we weren't happy with that. We built a bigger one, which is this can simulate up to 40 meters of liquefiable soil. Just as a quick throwaway comment, I'm going to say here, the world's largest shaking table is in Japan, in a place called E-Defense Facility. The E-Defense Facility has the largest shaking table, and you can have something like 6 or 7-story building constructed on the shaking table and shake it and fail it. And they can shake it in 3 directions and get it to fail. The biggest box with soil you can put on that can only go up to about 6-7 meters of soil depth. So, just the structural frame, they can test up to 7 floors. But if you make a box like this, big box, and fill it up with sand, the maximum sand before you reach the capacity of the shaking table is about 6 to 8 meters. Okay? The reason is soil is bloody heavy stuff. So even the largest shaking table in the world cannot handle more than 6 meters of soil, whereas a tiny little box like this can simulate 40 meters of liquefiable soil depth, which is more than what you need. And that's a big thing to remember. And it's an unfortunate thing that we're all in soil mechanics, but soil is complicated in so many different ways. It's not only because plastic, it's heavy. Everything seems to work against us, but we are quite ingenious bunch. We work around all the problems. Okay? We also have, for other problems, I'm showing all this because when I talk about some of the experiments later on, each will be in a different box, and there's a good reason why we use separate boxes for separate things. This is a laminar box. Now, another way you can think of modeling your semi-infinite boundaries is say my boundaries have no stiffness. That is, if the soil wants to go to the left, it can go to the left. If it wants to go to the right, it will go to the right. My box will simply follow. So what we did was to have these lamina. Each is a, as you can see, frame, and we have bearings in between the frames, which means to move it horizontally, you need almost no force because they're all on bearings. In fact, we are building a new version of this now. I hope they are doing well. I'm here. This is similar in terms of numerical analysis to having your end nodes of the finite element mesh tied together. It's quite easy to do in the FE because you can say the left node will have the same displacement as the right node at the same height. So tying the end boundaries is same as having a laminar model painting. This is particularly important if you want to study ground which is on sloping, of sloping nature. Yesterday I shown you plenty of examples of lateral spreading, but if you want to model that, this ESB box that I showed before is useless because the soil wants to flow from left to right, but the boundary will not let it do that. It will stop because it has some stiffness. Whereas this one will simply deform. There are some safety end stops on the right. Just about here you can see them. So if the box goes too much, it will stop it from coming off the centrifuge. Of course, you don't want the box to disintegrate and fall everywhere on the centrifuge. That would be disastrous. So we have these end stops as a safety feature. But again, this is something you want to think about, even if you're thinking of doing 1G shaking table tests. Boundaries are very important. Okay, I'm going to talk about one example, which is not to do with piles, but it's quite complicated and it has some significance. There are many problems, of course, we modeled over the years. As I said, even the SAM actuator produced a 12 PhD. So there are many aspects we have looked at. But this is the most complicated of the problems. This is not glamorous. It's to do with municipal solid waste. Now, the reason I picked this example for today is to show where the rest of the countries are compared to where we are. And I speak of this because I know people like Professor Ramana in IIT Delhi are working really, really hard to make this problem known. You must have heard this word municipal solid waste and landfills. Now, in most countries, it's illegal to have waste in landfills unless the landfill has at least 2 layers of protection. Because we all recognize once you put all the municipal solid waste in one location, it produces, due to chemical reactions, what's called leachate, and all the leachate will come to the ground, to the base. And if you don't have liners, it will go into the groundwater. It seeps, mixes with groundwater, and people will fall in. So to stop that, you need to have a clay liner, which is about, typically they're about 1 to 2 meters in thickness, all the way. I mean, these are not small things. You're talking about each cell of a landfill is about 200 by 300 meters. It's a massive, massive things. And you pile the waste maybe up to 50 meters high. So they are really, really big structures. So the vertical stresses are big, and the liners must be able to take the mechanical stress. The second line of defense you normally go for is a geomembrane. So above the landfill, you'll have a geomembrane that is covering. So in case there is a crack in your clay liner, you have a second line of defense. Many of these landfills are designed with a design life of about 50 years because we expect most of the chemical reactions to finish, biochemical reactions to finish in 50 years. Now, I mean, we are at a stage we want to design these and construct in India now. If you go to United States, particularly the West Coast, they have been doing this for the last 50 years. So they have lots of landfills which are reaching 40, 50 years is one problem. The other problem is they are short of land, particularly in the Bay Area, in and around San Francisco, San Jose, what you call Silicon Valley. So the land prices have gone up, which means they don't want to leave the landfill alone. They want to try and use that land to maybe put some low-grade warehouses and so on. So you want to go back and reclaim and use these now. The problem is these landfills have been sitting there for the last 50 years and they've been seeing many, many earthquakes, small earthquakes, big earthquakes over a period of time. Nobody knew what these earthquakes were doing to the liners of the landfill. And we wanted to investigate that. So obviously quite a challenging problem. So I thought I'd talk about this. So what will the earthquakes do? Will they crack the liner? Will the leachate escape? What's going to happen? And especially if I'm going to liquefy parts of this soil below or on the sides. So we created a fairly daunting centrifuge model that looks like that. Of course, we want to measure the tension in the geomembrane. So we had to have a mechanism by which we can have load cells at the end to measure the tension. So this fairly horrible looking contract. So that's my clay liner. That's just the model waste. And this is liquefiable sand. And initially we applied 0.15 G and 0.25 G as to sinusoidal earthquake. Because here you really want to damage this thing to see what it does. And lots of instrumentation, accelerometers, low pressure transducers, and so on. This is quite an old test, but even here we made a little webcams were just coming on market. So one of the things we like to do in my lab is to buy whatever is new and try and use it on the centrifuge. Often they might break, but compared to the cost of the centrifuge, the cost of a webcam is nothing. So we try these things. So they put it in a brass casing, but this is the first time we started getting images of what's going on immediately after liquefaction. So that's a new thing we did for this. So we could see how the clay liner was moving after the soil has liquefied. Basically, what happened was this stuff liquefied, and we were thinking that, oh, this will crack over here, or the weakest point is the junction, and you'll get all this leachate coming up. But the mechanics is quite different, and that's what the centrifuge will tell you. What this stuff all liquefied, and it had great weight on the waste does not liquefy, so it is still there applying the pressure. So all it did was to push this inclined liner into the liquefied soil. Liquefied soil has nowhere to go, so it has moved up. So after the test, what we saw was that this soil ended up here. So this moved up compared to the previous picture. So we could see from the LVDT measurements, this particular vertical settlement thing is actually showing a heat. So it's going up, while the one here is basically moving in. So that goes in, this goes up. It's almost like a undrained event where the volume has to stay constant. So if I push one end, the other end has to go up. And the pore pressures we could record also. The camera I showed you has recorded the, there should be a video somewhere, but I'm not going to play it. But you could see water coming up behind the clay liner. You can see just the damp patch there because this was taken after the test was finished. But clearly during shaking, you could see water come up. So, for a complicated problem like this, using centrifuge testing, we were able to understand how the lining forces have changed during shaking. And one of the biggest things that came out of this research was that every time there's an earthquake, you get extra tension in the geomembrane, and that does not go away. It stays. So earthquake after earthquake, we kept applying, and you could see the residual tension going up and up and up. And there's a very nice paper about this in Geotextiles and Geomembranes, I believe. If you like, you can have a look. But what other experiment in the world can you do which will tell you in a complex system like this what's happening under really complex load? And that's the power of centrifuge testing. So we shall use this technology and deploy it to our world of pile foundations and see what new things it can tell us. which you immediately may not think of. Okay? Tea time? Yeah? 11. Okay, then I can start. I can move it. Okay, let's have a 5-minute break and I'll reload it. By the way, if you have any questions, feel free to ask, as I said yesterday. So before we start, I can continue. Before I start pile foundations, are there any questions either yesterday or today so far what we have covered? Am I such an excellent lecturer, or are you being modest and not asking any questions? Surely nobody is that good. Everybody has.
There are some check tables where we can apply real Webcam also.
Mhm.
Then why is it required reduce modeling?
No. We also can apply real motions. It's about in a real shake table, you cannot have as much soil as you can have in a centrifuge mode if you apply the scaling laws. And if you, unless you make the models in the say 1G shaking table, the shaking table, if you have say a model only this big and put it on the shake table, then the soil in that model is not going, it will behave like a half a meter thick sand. It won't behave like a 10 meter thick sand layer. And that's the key. That's why we need the centrifuge. Yeah?
So in centrifuge testing, when we are carrying out some soil structure interaction problem, as you were saying that the frequency is scaled in time.
Yeah.
So how is the damping taken care of?
Oh, you need to, that's a good question. I have a PhD student who's looking at viscous dampers in structures, and we're looking at what effect soil structure interaction has on how structural engineers design viscous dampers. And you need to scale the damping as well. So you design the dampers to allow to, you're talking about structural damping.
Structural as well as soil damping.
Soil damping is automatically accounted for because you have the same material at the same stress. You will do the same stress strain loop as the real soil would. So, on as far as the soil is concerned, we are on strong ground. So, you'll get the same material damping. You'll get the same.
Sometimes damping is also frequency dependent, right?
Yeah, you mean the number of loops, but you work out the energy per cycle anyhow. When you're working out damping, usually what you tend to do is no board here. It's behind. That's great design.
Here it is.
Sir,
Okay. I can use that one.
So please
You
give
have
your
to
name
stand.
of-
at the corner of the
Okay. So normally the way you define wheels. Yeah, this the poster is falling apart. You may as well cover it up with this. Okay. So typically you plot your loops like this. And the area inside is the energy that's being distributed, right? So, but this is cycle by cycle. If you look at something like the Mason's law, what you say is that that area you work out, and you'll normalize that with so you join this point to that point, and you draw this triangle. So my damping is normally defined as, I don't know what symbol you use, let me use eta, is area of the loop or area of the band. And this works fine for solids. Because our material, or even with the pore pressure generation, these loops are changing all the time. We can work out cycle by cycle how damping is changing. And what starts for dry sand as maybe 7-8% damping, once you liquefy the soil, because the loops have fallen down, you can get something like 20% damping. Okay, 20 to 30%. So that bit is okay. You can ask the more pointy question you could ask is you're substituting the fluid from being water, which has 1 centistroke viscosity, to a fluid which has 50 centistroke viscosity. So really, my viscous damping is going up, right? And that is a trick question to answer. So to prove that this was raised even my PhD time. So what I did was I did 2 identical experiments with my power structures and so on. One was saturated with silicon oil and one with water. And we looked at the damping in the structure and in the soil for both. And it turns out that this bit is the most dominant of the damping. So damping typically has 3 components. One is, so the overall damping will be N meter material, which is this, plus eta viscous plus eta radiation. And what you can show is these 2 components are quite small compared to our material damping. So those get drowned up in the by the big number. So if I add small numbers to big number, the big number always dominates, right? So turns out that the viscous damping therefore does not play a big role in these type of large strain problems. Whereas if you did this very nice piece of work by a guy called Wilson and Bolton, it's a very nice paper, who showed that the viscous damping is quite big and in resonant column tests. And the reason they found that was the strains in resonant column tests are very small. Okay, so we are okay in the damping. As far as the soil damping is concerned, this is all good. But when you try to model the damping in the structure, then you need to be careful that your model structures you're building not only have their eigenfrequencies 10 times bigger, but the damping also need to be proportionally modeled. Typically use rally type damping, so there's an alpha m plus beta k. So you choose your alphas and betas until you get the right response in the right frequency range. I had to learn quite a lot of structural dynamics, obviously, to do this properly. Okay. Any other question? Yeah, sorry.
We still have to do shake table test for pile foundation. What suggestions you have to precautions?
Suggestion, somebody else was asking this question earlier. It's really tricky to do that. Any problem, unless you have really large shaking table where you can carry significant amount of soil. Most shaking tables I see are about this big. You only can make containers that big. And what piles are you going to use? Most people make these piles with say aluminum or something like that. Now, if you think of the stiffness of the soil, what's the most important thing in all this is the relative stiffness between the pile and the soil. So if you have a model where the way the centrifuge deals with it is your pile is made of aluminum. You can work out EI as we did yesterday. You have a scaling law for it, and the stiffness of the soil is increasing with the G level. So the relative stiffness between that pile and the soil is right, or at least approximately right. If you do the same thing at 1G, the stiffness of the pile is up there, and the stiffness of the soil is down here. So the contrast is really, really big. So you cannot compare the behavior of this to prototype. Having said that, I also do 1G testing. Okay, where you can make some use of 1G testing is comparing one test to the other. Don't think of your 1G model as some scaled down version of something big. That won't work. Okay? But it is still a physical reality at the scale you are testing. So it is a physical model. So if you treat it like that, then you can compare one test to another, and then you can make some conclusions from that. But be very clear in your mind, and if your supervisor is not agreeing, send him my way. I will sort him out. Please do not try to compare what is done at small scale to large scale. That is where everybody gets into trouble. Best thing is to simply take it as a physical reality, and some useful things can be done.
So, can we still relate the failure mechanisms?
No, that is the problem. Unless you need to be really innovative. Okay, think of, okay, I can't increase the stiffness of my soil. Maybe I can drop the stiffness of the pile. Maybe I will make a plastic pile, okay, or a paper pile, whatever the right material is to drop the stiffness. Now, if you realize that what is governing is the relative stiffness between the pile and the soil, then there are other ways you can do that. Again, that will help you capture more close to the right behavior, but not the exact one. And scaling is always an issue. I'm sorry, I can't give you a more satisfying answer, but that's the truth. And that's why people spend millions of dollars building this big shaking table. So but centimeters are not like millions, they're quite cheap. So, it's only $100,000. So. Any other question? Okay. I got about 15 minutes. Let's start looking at the pile foundations. Now that I got bored as well, I want from the audience, how do you think people design pile foundations? Or how do you do it? You're engineers. If you have to design piles for a structure tomorrow, what do you do? What are the things you need to know? Anybody? It's all done.
Vertical.
Geotech 1, Geotech 2, all modules, right?
In situ test results.
Sorry?
In situ test results. Soil
In situ
problem.
test results. What in situ test would you do?
Cone penetration test.